So maybe we look at the second example first, which is easier. Okay. So in this example, we plot the group delay characteristics for these telephone lines, this long distance telephone lines in the United States. Okay, so this is a study made in 1971 by AT&T in the States. Okay, so here we have the group delay versus the frequency. Okay, so different frequency observes different group delay, and you have two curves here. One is for medium distance, and one is for short distance. Okay, so for short distance, the group delay is usually less severe than longer distances. Okay, but regardless of whether you're looking at short or medium, the point is that at different frequencies, you see a different delay, right? So you see smaller delays at frequencies around 1800 hertz, but you see larger delays at low frequency and also at high frequency. Okay, and this is just the corresponding magnitude spectrum. All right. Now, if you look at the impulse response, what is the impulse response? The impulse response is what you get at the output when you insert a delta function inside. Okay. Now, a delta function has a flat spectrum. Okay. A delta function, if you remember, a delta function has a flat spectrum. Okay. A flat spectrum means that it has equal frequency components at all frequencies. Okay. Now, what this tells you is that when you insert this delta of t inside, you will experience different delays for low frequency and for high frequency components. Okay? And intermediate frequency components experience less delay. So what would you expect at the output? Okay. So when you send this delta, right, through this telephone line, right, then at the output, you receive different frequency components at different times. So they are no longer aligned perfectly to get this, really sharp delta function at time 0. But instead, you will see some signals rippling, arriving later. Okay. So this is what you observe at the output. So again, remember, this is what you send, but this is what you receive. Okay. So because different frequency components are now dispersed, right? Some arrive later than others. Okay. Therefore, you no longer just see a delta, but actually signals dispersed over time. Right? And in fact, if you look at what arrives later, you will see that the part that arrives later has really low frequency components and also really high frequency components. Okay? And this corresponds to the fact that low and high frequencies have a large group delay. Okay? Okay, so this is another example with more actual numbers. Okay, so here, suppose that you have three linear time invariant systems, right? H1, H2, and H3 with frequency response this, and you put them in series, right? You cascade the three of them together so that you get a system with effective response that is equal to the multiplication of the three. Okay. Now we want to look at the magnitude and phase of the frequency response. Okay. So if you look at this, you can actually write it. Suppose you view the numerator as A and the denominator as B. Okay? So then you can write this as the magnitude of A times e to the j, the phase of A, the magnitude of B, and e to the j, the phase of B. Okay? Now the magnitude of A is 1 plus j omega I squared, this whole thing squared, minus 4 zeta squared omega over omega I squared with the square root. Okay? So I'm just taking the square of the real part, right? So I think I should have a plus sign here. Okay. So the magnitude is just the square of the real part plus the square of the imaginary part. Okay, with the square root. And you can see that this is actually equal to the magnitude of B. Okay. All right. And then what is the phase? Okay. The phase is arctangent, yes, arctangent of the imaginary part divided by the real part. Yes, very good. Okay, so it's arctangent of minus 2 zeta I omega over omega I over 1 minus, let's see, okay, 1 minus omega over omega I squared. Okay. So it's arctangent of the imaginary part divided by the real part. Okay. So we can actually bring the negative sign outside to get this. Okay. And if you observe B, you will see that B is different only by the sign here. So B actually has a phase that is equal to minus the phase of A. Okay? So then the magnitude of HI is just the magnitude of A divided by the magnitude of B, which is 1. Okay? And so, and then the phase, okay, the phase of HI is just the phase of A minus the phase of B. Okay? Okay? And if you plug this in, this will be minus 2 times arctangent of 2 zeta I omega over omega I over 1 minus omega over omega I squared. 这个吗？这是 zeta 啊 zeta 我不知道是不是有英文拼音啊，不过反正就是念 zeta 啊。OK. Okay, so here we get the magnitude of each one of these responses and also the phase, okay? So if you look at the overall H, right, the magnitude of H is just the product of the magnitude of each one of these, and it would still be 1, okay? So the magnitude of H is just the product of each one of their magnitude, which is 1, okay? And the phase of H is just the summation of the phase of each one of them, okay, which is summation minus 2 arctangent, what is it? Okay, zeta I omega over omega I over 1 minus omega over omega I squared. Okay. Now, what is this? What does this term give you, right? What is the shape of this term? Okay. So we know what tangent looks like, right? Tangent x is something like this, right? It goes from minus pi over 2 to pi over 2, something like this. Okay. So if you take arctangent, right, then infinity corresponds to pi over 2, minus infinity corresponds to minus pi over 2. Okay. So suppose you start from 0. Okay. Suppose you start from 0. Then this arctangent is 0, right? But as you increase towards omega I, as you increase, omega increases towards omega I, this denominator becomes larger and larger and eventually to infinity, right? So as omega approaches omega I, right, this denominator becomes bigger and bigger and eventually to infinity, right? Because if omega is equal to omega I, then 1 minus 1 is 0, okay? So when you have this going to 0, this entire thing, right, goes to infinity, and arctangent of infinity is pi over 2. So pi over 2 times minus 2 is minus pi. So what you get is something like this. You start from 0, and then around omega I, you arrive at minus pi. Okay. But then once you go a little bit beyond omega I, this term becomes larger than 1, so this becomes negative, but still close to infinity, right? So this starts from minus infinity, right? Which minus infinity gives you, corresponds, arctangent gives you minus pi over 2. Minus pi over 2 times minus 2 is pi. So you go from this point here, which is at minus pi. Once you increase beyond omega I, you jump to pi, and then you start decreasing again as omega increases. Okay? So you get something like this for each one of these terms, right? Now, in this particular example, we're looking at the case where we have 3 of these, each one at frequency, 315, 943, 1888. And this is in radians, but if you convert it to hertz, this is at 50, 150, and 300 hertz, okay? So you have something like this at 50, have this discontinuity at 50 hertz, 150, and 300, okay? So when you add them together, this is what you get, all right? So you have this phase with a jump at 50 hertz, 150, and 300 hertz, okay? So this is a jump occurring at 50, 150, 300, and this is jumping from minus pi to pi, okay? Right. So this is the phase of the effective system that you get. Now, suppose you want to find the group delay. The group delay, you need to take the derivative, but this may be a little bit difficult at the discontinuity points, okay? But actually, for the phase is equivalent up to a modulo 2 pi, right? So I can actually, add, shift any point by 2 pi, and it will not change the response of the system, okay? So what I'm doing here is that for this block, I'm moving it down by 2 pi so that this point now connects with this point, okay? And then so that I get, right, this goes from 0 down here, and then if I move this down by 2 pi, it should connect with this, so we continue down. And then we move this point down by 4 pi, and it will continue to connect with the previous curve, and this by 6 pi to get this, okay? So we're sort of folding, refolding this spectrum so that it now becomes continuous. And then by taking the derivative, we get a group delay like this, okay? So you can see that for this system, you have very large delays around 50, 150, and 300 hertz, okay? All right, so this is obtained by, unwrapping by multiples of 2 pi, right? And then by taking the derivative, okay? Or let's say minus the derivative. All right. And you see that you have, these large delay values at the 3 frequencies. And in fact, the largest delay occurs around 50 hertz, okay? So if you look at the impulse response, okay, you will see that even though you insert an impulse into the system, these 3 frequency components will actually be delayed more at the output. And in fact, 50 hertz, which is the lowest frequency, is delayed the most. So at the end, you see only this low frequency component, right? But 150 and 300, even though they are delayed, they're not delayed as much as this one, right? So these are just examples to show you how, this group delay caused by the nonlinear phase of the system will distort the output of your signal. Okay?你说哪边？对，这个是相乘的符号。对对对。这个大家是第一次看到吗？还是比较少看？第一次看到。OK。好。没关系，这个所以对啊，谢谢你问，因为好像显然很多人不知道，我不知道你们不知道这样。OK。好。好，所以到这边有没有什么问题？OK。Right. So these are just some examples to show you what is the effect of a nonlinear phase of the system. Okay. All right. So going back to the magnitude and phase representation of the signal and also of the system. Okay. So instead of writing, right, if we want to really actually visualize this magnitude and phase, instead of plotting the original magnitude, okay, instead of plotting the original magnitude, which takes on this multiplicative relationship, we often like to, take the logarithm of the magnitude instead, because if we take the logarithm then of the, let's say, take the logarithm of this magnitude of y, we will get the logarithm of the magnitude of h plus the logarithm of the magnitude of x. So by taking the logarithm, I get a additive, relationship instead of a multiplicative relationship. Okay, and addition, for us is often easier to visualize than multiplication. Okay, so when you want to plot out this magnitude and phase of the system, we're more accustomed to plotting the log magnitude rather than the magnitude itself, so that it has an additive relationship similar to that of the phase. Okay, so this is one advantage. And another advantage is because if you draw something in log scale, you have a larger dynamic range. Okay? All right, so but instead of just taking a simple log, we actually take 20 log 10, which gives you a unit of what we call decibels. Okay? So instead of just looking at log magnitude, we take 20 log 10, the magnitude, which has a unit of decibels. Unit of this thing. Okay? So you must have seen this in your other classes, right? Like in circuits and systems or things like that. Okay. So 有多少人是第一次看到这个 dB 的？有没有 ？OK， 那有看过的，就是在什么课里面看过？电路嘛，对，电子也有。OK， 所以在这个比如说电路课或是这个 system 的课，可能会有更多的一些 interpretation 啊。不过基本上在这边的话，它就是一个，你就把它看成是一个定义这样子。我们就是会习惯去看这个20 log 10的这个 magnitude。Okay. All right, so if you plot this 20 log 10 of the magnitude and the phase versus also the logarithm of the frequency, then what we get is what we call the Bode plot. Okay, what we call the Bode plot. Right. So this is an example of a Bode plot. Okay, so we have 20 log 10, the magnitude, versus the logarithm of the frequency. Okay, and this is the phase versus the logarithm of the frequency. Okay. Now we often can just plot the positive frequency because if your impulse response is real, which is often the case in practice, then we know that the magnitude is even and the phase is odd. So given what it looks like in the positive frequency, you can infer what it looks like in the negative frequency. Okay? Okay. Now, when you express the magnitude in decibels, right, there are some typical values that you may be interested in. Right. For example, when you see people referring to, let's say, 0 dB, then when would you get 0 dB? Right? You get 0 when this magnitude is 1, right? Because log 1 is 0. Okay. So when you say you have a system with a gain that is 0 dB, then this corresponds to a gain of 1. Okay? Now, when you have a gain of 20 dB, then this corresponds to a gain of how much? Okay. Of 10, right? Yeah. So you have, if this gain is 10, then log 10 is 1, so 1 times 20 is 20, okay? So 20 dB corresponds to a gain of 10, okay? Now what about minus 20 dB? Yeah, minus 20 dB corresponds to a gain of 0.1. Okay? Because 0.1 is 10 to the minus 1, right? So log 10 of 0.1 gives you minus 1. Minus 1 times 20 is minus 20 dB. Okay. Now another important value is 3 dB. Now why is 3 dB important? Okay. So 3 dB is important because it corresponds to a gain of 2. Okay. So if you plug this value 2 inside this 20 log 10, then you will get a value that's approximately 3. Okay? All right, so these are some values that you will see more often. Okay. Okay, so if you observe this Bode plot here, right, you have this 20 log, the magnitude versus the frequency. You can see that you maintain 0 dB, which is about unity gain at low frequency, but then the gain starts to decay really fast, as you go towards higher frequency. Okay. All right, so this is the Bode plot for continuous time signals. Okay. Now, when you have discrete time signals, you can draw something similar, but for discrete time signals, you wouldn't want to plot the frequency in log scale, because for discrete time signals, the frequency is only confined within a 2 pi range. Okay, so there's no sense of drawing the log scale. Okay. So for discrete time, you would just plot this out in linear scale of the frequency, and this is just an example for the 20 log 10 of the magnitude and the phase. Sorry. OK， 所以我应该要讲那个根号2。OK， 那为什么我刚才讲2？是因为就是 3 dB 通常是对应到你的 energy 的2倍。OK， 但是我这里是只有看那个 gain。我这里是只有看这个 gain， 就是如果 energy 的话，就要有一个平方。OK， 谢谢。Okay. All right, so like I mentioned, for the discrete time case, we use a linear scale. Right, linear scale suffices because we're confined only to a 2 pi range. Okay. Now, one of the biggest motivations for studying this time and frequency relationship is for the study of filter designs. Okay, so for example, we looked at previously the design of frequency selective filters, for example. Okay, so we showed that suppose you look at this ideal low-pass filter, right, which has this frequency response that looks like this. Okay, so if an ideal low-pass filter lets through frequency components perfectly between minus omega c to omega c and shuts down everything beyond that. Okay, and you have something similar in discrete time as well. Okay, but when you insist on using an ideal low-pass filter, right, that takes on this perfect shape in the frequency domain, you would have a time domain impulse response that looks like this. Okay, and this is very difficult, or actually impossible to use in practice because of the various reasons we mentioned previously. All right, so first of all, this impulse response is non-causal. Okay, you cannot really implement something in practice that is non-causal, and you get these ripples that decay really slowly, and it's just really difficult to well approximate this shape using practical circuits. Okay, so there are different, even though you get perfect stop bands and pass bands, and actually, there is no phase distortion. Right, the phase of this signal is 0. Right? But actually, it is not implementable in practice. Okay. Now, sometimes when people look at an ideal low-pass filter, right, they may relax this a little bit instead of insisting on having 0 phase distortion, sometimes it's okay to have a linear phase accompanied with this perfect magnitude, okay? Because a linear phase just corresponds to a time shift at the output, okay? So if you see something like this, it is still considered an ideal low-pass filter because at the and this corresponds to a time domain had impulse response that is just delayed by a certain amount, okay? But because even with this linear phase shift, okay, this ideal response, still gives you all these, problems in the time domain, okay, regardless of the phase shift, regardless of the time delay, okay. So in practice, right, this is the step response, okay. So in practice, you cannot have an ideal filter. But you can only design things that are as close as possible, okay? So in practice, you cannot require the designer to design a frequency response that maintains flat in the pass band, goes to the stop band, immediately, and then stays 0 in the stop band, right? So in practice, to design practical filters, you must allow some tolerance, okay? So you must allow some tolerance in the pass band, right? Allowing the gain in the pass band to vary within a certain range. You must allow a little bit, okay, of variation in the stop band, meaning that you allow a little bit of these frequencies inside. And the transition from the pass band to stop band, right, can never be immediate. Right? You have to have a range for your filter to go from a pass band to stop band. Okay? And how strict you impose this constraint on this range or on the transition time will affect the corresponding characteristics in the time domain, okay? So how strict you pick these values will correspond to, for example, how fast this signal rises in the time domain, how much it ripples, and how much time it takes for you to settle down to a region of value that you're satisfied with, okay? So I'll talk a little bit more about this next week.